Hello friends, in this video we are going to discuss about the character table. How can we solve the character table, or we can say how we can use the character table for finding out the total number of vibrational degrees of freedom for a given molecule. So for this we will take the example of BCl3 molecule, and we know that the shape of the BCl3 molecule is trigonal planar, as the boron atom is sp2 hybridized, and for this the point group will be D3H, because we have a C3 axis which is the principal axis, and there will be 3 C2 axis perpendicular to the C3 axis, and we will also have 3 sigma V planes and 1 sigma H plane. So the point group will be D3H. So here it is the character table for the D3H point group. On the extreme right hand side of the character table we can see there are 2 columns mentioned as IR and Raman. This tells us about the spectroscopic data, or we can say which mode is IR active and which mode is Raman active. Here we can see there are capital R. Here capital R denotes rotational modes, and this small x y, this denotes the translational mode. So this capital R, these terms denotes the rotational degrees of freedom, and these coordinates x, y and z denote the translational degrees of freedom, and these quadratic terms denotes the Raman active modes. But there is no mention of the vibrational degrees of freedom, so we cannot find out the vibrational degrees of freedom directly from the character table. So we have to solve this character table and find out the reducible and irreducible representations, and finally we'll come out with the vibrational degrees of freedom. So we will see how we can solve this. So first of all, we know that the total number of degrees of freedom in any molecule is trizen, where n is the total number of atoms. So for this molecule there are 4 atoms, so therefore the total degrees of freedom will be 12. Okay, so the total degrees of freedom is 12. So in order to find out the vibrational degrees of freedom, we have to find out the reducible representation for this character table. So we have to make one table where we will write all the symmetry operations, and we will have to find out 2 terms, the number of unshifted atoms and the contribution per atom. So the number of unshifted atoms, how we can find out? We will apply all these symmetry operations on this structure of BCl3, and we'll check how many atoms remains unshifted, or else we can say how many atoms does not changes its position after the symmetry operation. So for E operation, we all know that all the atoms will be unshifted, will remain unshifted. Okay, because it is the identity operation, because after this operation the molecules remains as it is. So that's why the total number of unshifted atoms will be 4. For C3 axis, if you see that the axis passes through the boron atom and it is perpendicular to the plane of the molecule, so the boron atom will remain unshifted and all other chlorine atoms will change its position by 120 degree. Okay, so only one will be the unshifted atom because it will be the boron atom. For C2 axis, we know that the C2 axis will pass through this CLB bond, chlorine and boron bond, and the other 2 chlorine atoms will rotate and change its position. Okay, so their unshifted atoms will be 2. The sigma H plane is the plane of the molecule, and it will be as we know that the structure is planar, so all these atoms will be unshifted. Therefore the number of unshifted atoms will be 4. For S3 we know that it will be similar to that of C3. For S3 we know that is rotation followed by reflection in a plane perpendicular, so it will come out to be 1. Okay, you can simply write that the whatever unshifted atoms you get for the principal axis, you write it for the improper axis of rotation, and whatever you get for the C2 axis, you can write it for the sigma v plane. We can also check out that this, if we put the sigma v plane, it will, this plane will pass like this. It will bisect the other two Cl atoms. So because these two atoms will get reflected, that's why only two atoms will remain unshifted. Okay, so in this way we can find out all the unshifted atoms corresponding to these symmetry operations. Okay, next we have to find out the contribution per atom. So for finding out the contribution per atom, you have to use two formulas. For the Cn axis we will use the formula 2 cos theta plus 1, and for Sn axis, that is the improper axis of rotation, we will use the formula 2 cos theta minus 1. And always remember, for any sigma plane the contribution will remain 1, and for the E element, E operation, the contribution will be 3. Okay, so for E operation the contribution will be 3. For any sigma plane the contribution will be 1, and for this C3 for the C3 axis we know that the theta will be 120 degree, so cos theta will be, cos of 120 will be minus half, so minus half, the 2 will get cancelled, it will be minus 1 plus 1, it will be 0. Okay, and for C2 axis cos 180 it is minus 1, so it will come out to be minus 2. Cos 180 is minus 1, so it will come out to be minus 2, and this is plus 1, so it will be minus 1. Okay, and for S3 we know that it is 120 degree, 120 will be minus half, so 2 will get cancelled, minus 1 minus 1, it will be minus 2, so the contribution will be minus 2. So after finding out the number of unshifted atoms and the contribution per atom, we will simply multiply these terms. Okay, after multiplying these terms we will write it on the next row. Okay, below this, so it will come out to be 4 into 3, it will come out to be 12. 1 multiplied by 0, it will be 0. 2 multiplied minus 1, it will be minus 2. 4 1, it will be 4. 1 minus 2, it will be minus 2. 2 into 1, it will be 2. So this is simply the reducible representation. One more thing, this will only be the reducible representation only if this value, if this value, if the square of this value is greater than the order, then this can be the reducible representation, or we can call this as the reducible representation. Always keep in mind that we have to square the term under E, square the value under E, that is 12. 12 square is equals to 144, and it is greater than 12, which is the order of the character table. Okay, so if this value is greater, if the square of this value is greater than 12, then only this will be the reducible representation. So now you can think what is order and how can we find out the order. So simply we know that the order is simply the sum of all the coefficients of the symmetry operations. If we add all the coefficient of the symmetry operations, then we will get the order of the character table. So here it will be 1 plus 2 plus 3 plus 1 plus 2 plus 3, it will be 12. So order will simply be 12. And class, how can I find the class of this character table? The class of this character table will be simply equal to the number of symmetry elements. So here 1 2 3 4 5 6, there are 6 elements, so class will be 6. So in this way we can find out the reducible representations. So after finding the reducible representation for this character table, now we have to find out the irreducible representations. So before finding the irreducible representation, we will simply write the reducible representation under this character table. So first of all we will find out the irreducible representation for this Mulligan symbol A1 dash. So how we will find? We will simply multiply all these terms. For A1 dash you have to multiply this reducible representation value with this one and the coefficient of the symmetry operation. So here it will be 12 multiplied by 1 multiplied by 1, because the coefficient is 1. Then we have to plus sum plus, and we will multiply 0 then 1 with 2, 0 into 1 into 2. So next it will be minus 2 into 1 into 3, minus 2 into 1 into 3, then it will be 4 into 1 into 1. So in this way we will sum up all the products, sum up all these parts, and then we will divide the result of this part with the order, okay, which is 12. So then after that we will see that it will come out to be 1, okay, for this A1 dash Mulligan symbol. In this way, similarly, we will find out all these Mulligan symbols, all these values in a similar way. Therefore, if you can see it for A2 dash, we can simply, it will take 12 into 1 into 1, because 12 into 1 into 1, then 0 into 1 into 2. So for these it will always come out to be 0, because anything multiplied with 0 is 0. For this one also, E, if you can see this one, for the E dash, here it is a 0, so it will come out to be 0. For E double dash also there is a 0, so it will come out to be 0. And then this one also it is 0, here also it is 0, so it will come out to be 0. And in the same procedure if you follow, and we will find out all the characters for these Mulligan symbols, okay. So after that we will write the irreducible representation as A1 dash plus A2 dash plus 3 E dash plus 2 A2 double dash plus E double dash. So this is the irreducible representation for this character table. So the irreducible representation will come out to be this one: A dash plus A2, A1 dash plus A2 dash plus 3 E dash plus 2 A2 double dash plus E double dash. So from this irreducible representation we have to subtract the rotational and the translational degrees of freedom. So from the character table we know that the rotational degrees of freedom are A1 dash and E double dash. So it is this A1 dash, A2 dash and A2 dash will cancel out, and E double dash and E double dash will get cancelled out. And for the translational degrees of freedom we will get E1 dash and this A2 double dash. So this A2 double dash will come cancel with this one of this A2 double dash, and E1 dash will cancel with this, and 2 will remain. So after subtracting the rotational and translational degrees of freedom from the irreducible representation, we will get the vibrational degrees of freedom as this, okay, A1 dash plus 2 E dash plus A2 double dash. Here A1 signifies 1 because it is a non-degenerate, and this A2 will also be non-degenerate, so it will be 1, and this E means it is a doubly degenerate, that means it signifies 2, and already there is a 2 in the, and there is a 2 E dash, so therefore it will be 2 into 2, so it will come out to be 4. So overall the total number of vibrational degrees of freedom will be the total, therefore total number of vibrational degrees of freedom will be equal to 4 plus 1 plus 1 will be equal to 6. So there will be 6 vibrational degrees of freedom, okay. And out of these 6, this one is IR active, this one this A1 dash you can see it is Raman active, this is Raman active. This A2 double dash it is IR active, and this E double dash E dash is both IR and Raman active. This is both IR and Raman active, okay. This mode of vibration is about iron and Raman active. This is iron active and this is Raman active, and this E is about iron and Raman active. So we have to find out the so we found out that the total number of vibrational degrees of freedom corresponding to BCl3 molecule is 6. Now we can also find out in a simple way, as we can know that the formula for any nonlinear molecule, the degrees of freedom is given by 3n trisn minus 6. Okay, so trisn minus 6, here n is the number of atoms, so it will be 3 into 4, 3 multiplied by 4 minus 6, so it will come out to be 6. Simple. So after verifying this, we can see that that our answer is correct, and the process is if we find out the degrees of freedom using this formula and this using the character table, it comes out to be same, so therefore it is correct. So you can simply try for some other molecules also using other character tables. For say you can use for C3V, C2V and D4H, any molecule you can try it and comment down below how is your experience. So with this I am going to end up this video. In the next video we'll check out some other topic, and if there is any doubt regarding this character table, group theory or molecular symbols, please comment down below and let me know how I can improve it. So with this I would like to end up my video. Thank you.